In this presentation, I wanted to talk about the parameters in fabrication process that affect the efficiency of the OFAT. The content of this presentation can be divided into two parts. First is the parameters or the indicators that are related with the device performance. Another one is the fabrication process and related to the charge transport properties and the overall efficiency of the device. At the beginning, we need to introduce the types of organic field effect transistor. Based on the positions of gate and contact, there are mainly four types of effect. First is the top gate, bottom contact, TGBC. Then top gate, top contact, TGTC. Bottom gate, bottom contact, BGBC. And the bottom gate, top contact, BGTC. It has been well accepted that BGTC and TGBC effect usually exhibit lower contact resistance than BGBC and TGTC. The first parameter is the thickness, that involves the contact thickness and the active layer thickness. Referring to the image, TC represents the contact thickness. In the commonly used bottom contact and bottom gate effect, thicker contact afford a large area for charge injection, but increase the consumption of contact material. Additionally, thick contacts cause inferior organic semiconductor molecular packing and thus degrade the charge transport at the contacts. There is a conclusion from the article below that in effect using poor quality organic semiconductors such as the polymer, relatively thick contacts facilitate charge injection and alleviate contact limitations to the overall charge transport. Another thickness is active layer thickness. Nowadays, the capability of printed equipment can typically reach to 100 meters and thin thickness of the deposit layer 100 nanometer. For the type of OFAT that source and drain contacts are formed on the opposite side of the semiconducting layer from the active semiconductor dielectric interface, the charge injected at the source and extracted at the drain need to cross the entire thickness of the semiconducting layer before reaching the active semiconductor dielectric interface. So a thinner active layer can result in improved charge transport as it reduces the distance over which charge carriers need to travel, leading to faster operation and potentially higher current carrying capability. The main influence of the thickness arises for the sub-threshold slope and the threshold voltage. A thick active layer may require a higher gate voltage to reach the threshold due to increased capacitance, making the device less sensitive to external control and potentially less efficient. We need to balance these two thicknesses. One research found that an increase in the contact resistance would arise from the semiconductor thickness be comparable to the thickness of the gold source and drain contacts. Besides, different OFAT configurations such as bottom gate and top gate devices may have different requirements for optimizing semiconductor and contact thicknesses. The selection of organic semiconductor is also a very important process for fabrication. Generally, N-type organic semiconductor shows a lower device performance comparing with their counterpart P-type organic materials. Conjugated polymers offer good charge transport properties, but their performance can vary based on the specific polymer structure. Some non-conjugated polymers are used as organic semiconductors in OFETs. They may exhibit lower charge carrier mobility compared to conjugated polymers, but have unique properties suitable for certain applications. Small molecules like potassium and ruberin are high-performance organic semiconductors that can achieve excellent charge carrier mobility. However, they are sensitive to some environmental factors and require precise deposition techniques. Fullerene derivatives like PCBM are often used as N-type semiconductors in organic solar cell, but can also be used in OFETs. They offer good electron transport properties. The choice between P-type and N-type organic semiconductors depends on the desired charge transport behavior. Doping can be crucial for tuning charge carrier concentration and improving charge mobility in OFETs. Dielectric is also an important factor. Dielectric requires high capacitance, low leakage current. An optimal dielectric organic interface facilitates smooth charge carrier injection, reduce trap states, and promote efficient charge transport. Charge transport begins with the injection of charge carriers from the metal or dielectric electrode into the organic semiconductor. This injection process is influenced by the energy level alignment between the electrode, the organic semiconductor, and the dielectric. For efficient charge injection, the energy levels of the electrode and the organic semiconductor must be well matched. Once charge carriers are injected into the organic semiconductor, they accumulate near the dielectric organic interface due to the presence of energy barriers that prevent them from freely moving deeper into the semiconductor. These energy barriers arise from the difference in the electronic structure between the dielectric and the organic semiconductor. Charge carriers accumulate near the surface. They can move through the organic semiconductor. The mobility of the charge carriers in organic semiconductor is relatively low compared with traditional inorganic semiconductors, and it is influenced by factors like the molecular structure, crystallinity, and temperature. In some cases, charge transport may occur while hopping between localized states or delocalized charge transport along conjugated polymer chains. Charge carriers can get trapped by defects, impurities, or trap states within the organic semiconductor. Trapped charges can lead to non-radioactive recombination, reducing device efficiency. Avoiding or minimizing traps is critical for achieving high-performance organic devices. So engineers and scientists often use various techniques to engineer the dielectric organic semiconductor interface to improve the charge injection, reduce trapping, and enhance charge transport. Another thing we need to notice is the organic gate dielectrics with strong polar groups can absorb water and experience a slow relaxation, which can compromise device performance. So when a gate dielectric is selected, attention should be paid to either eliminating this issue through selecting of a less hygroscopic dielectric material or by dehydrating and encapsulating the device. Contact resistance is a value that we are undesirable. Contact resistance at the source and drain electrode and semiconductor interfaces play an important role, which becomes increasingly important when the length of the channel is reduced and the transistor operates at low fields. Organic semiconductors often have energy levels that do not perfectly align with the work function of the metal electrodes. This misalignment can result in energy barriers at the organic semiconductor and metal interface, causing increased resistance to the flow of charge carriers. The quality of the contact interface between the organic semiconductor and the contact electrodes can be affected by the roughness of the surface. Irregularities and imperfections at the interface can hinder the charge transport, leading to higher contact resistance. The microstructure and the molecular packing of the organic semiconductor organic semiconductor layer can influence contact resistance. Poorly ordered or disordered molecular arrangements can create barriers to charge carrier injection and extraction at the contacts. Contaminants or impurities at the interface between the organic semiconductors and the contact electrodes can introduce additional resistance by blocking or scattering charge carriers. We should also consider the device geometry. The dimensions of the source and drain channel, also known as the length and the width, can influence OFET performance. Smaller channel lengths can result in faster switching speed, while wider channels can carry higher current. The aspect ratio, which is the length to width ratio, can impact both speed and current carrying capacity. From the article below, there is a finding that the shorter channel length, the bigger current of drain to source flowing on the OFET. The last parameter is the work function. The work function is a fundamental property of a material that characterizes the energy required to move an electron from the hormone level of the material to the vacuum level. Or fundamental, it is the gap between the Fermi level to the vacuum level. The gate source voltage, VGS, applied to the OFET determines the alignment of energy levels at the semiconductor gate interface. The threshold voltage of the OFET is the gate voltage at which charge carriers start to accumulate in the semiconductor channel. It is influenced by the difference in work function between the gate electrode and semiconductor. Besides, the electrode semiconductor interface is characterized by an injunction barrier due to a mismatch in the mental work function and the molecular orbital energy levels. So, work function has a strong relationship with the gate source voltage, threshold voltage, interface charge injunction, and etc. Work function affects the alignment of the energy bands within the semiconductor, influencing the mobility of charge carriers. So, a well-matched work function can lead to improved charge carrier mobility. In OFET design, selecting materials with appropriate work function for the gate electrode and the semiconductor is crucial to achieving the desired charge transport characteristics and device performance. Then we go into the second content, which is the fabrication. Here lists the general fabrication process. And we want to talk about the top 5 items, which is the substrate selection and the deposition, involving the gate electrode, gate dielectric layer, organic semiconductor, and source and drain electrode. The left side is the standards that we choose the substrate, and the right side is the common materials that we used for substrate. First is the silicon wafers, which is smooth and flat, have the good thermal conductivity, and it is chemical stability, but it is rigid and limited transparency. The second one is the glass. The glass is transparent and smooth, but it is brittle and limited flexibility. The third one is the plastic film. It is flexibility and light. but it is rough and sensitive to the moisture and oxygen. The first one is the polymer substrate. Also, it is light and compatible with the roll-to-roll process. However, it is also rough and some issues with the thermal stability. Last one is the paper, which is low cost and can be used for large area devices fabrication. The same issue is the roughness of this substrate. The substrate material should have good dielectric properties and compatibility with the dielectric material. Mismatches in dielectric properties can lead to charge trapping and affect charge transport. A smooth substrate surface is desirable to ensure uniform and continuous semiconductor film deposition. Surface roughness can introduce defects and scattering sites that hinder charge transport. Substrates with appropriate surface energy can facilitate the formation of uniform and well-ordered organic semiconductor films, which can enhance charge transport properties. Substrate materials with high thermal conductivity can help dissipate heat generated during device operation. Excessive heat can degrade organic semiconductors and lead to reduced charge carrier mobility. Next, we want to talk about the deposition. Generally, there are two types of methods. First is the thermal evaporation, while the other is the solution process. Thermal evaporation has low contamination rates and a well-controlled deposition rate. Solution process enables large-scale deposition and low-cost fabrication of devices. There are three depositions for making an OFET: gate electrode, semiconductor, source and drain electrode. Organic gate dielectrics. Just as mentioned before, it should be high capacitance. Besides, we can see this image that a rough gate electrode correlates with a rough gate dielectric and introduces structural distortion in the semiconductor film. This structural distortion, represented mainly by grain boundaries and their density, lead to the formation of transport barriers and trap states that have a detrimental effect on the electric characteristics. The deposition method and conditions will impact the device performance by influencing the molecular organization and the semiconductor molecules. A well-organized crystalline film typically results in better charge transport properties and higher charge carrier mobility. Deposition methods that promote a highly ordered and crystalline structure tend to result in higher mobility and better device performance. Besides, the deposition method influences the thickness and the uniformity of the organic semiconductor layer. The organic semiconductor layer can interact with the gate dielectric and the source drain electrode in an OFET. The quality of these interfaces can be influenced by the deposition process. For instance, certain deposition techniques may lead to the formation of unwanted interfacial layers or the defects that hinder charge injection and transport. Organic semiconductor deposition processes are sensitive to contamination from impurities, dust particles, or residual solvent. These contaminants can get trapped at the interfaces and introduce defects. The quality of the substrate and gate dielectric surfaces can affect interfacial layers. Insufficient cleaning or treatment of these surfaces may lead to poor adhesion and the formation of interfacial defects. In thermal evaporation, the organic semiconductor material is heated and vaporized before condensing onto the substrate. This process can sometimes result in incomplete coverage, discontinuous films, or defects due to variations in vapor pressure. Inkjet printed films may have smaller grain sizes and lower crystallinity compared to the films prepared by other methods like vacuum deposition. This can lead to lower charge carrier mobility and reduced device performance. Solution-based methods like spin coating can be prone to defects if the concentration of the semiconductor solutions, solvents, evaporation rates, and spin speed are not optimized. Excessive roughness of the substrate or the gate dielectric surface can lead to poor contact and defects at the interface. For source and drain electrode deposition, a smooth and defect-free interface promotes efficient charge injection and transport. Rough or contaminated interfaces can lead to increased contact resistance and charge trapping, hindering charge transport. The width and geometry of the source and drain electrodes can affect charge transport. Wider electrodes allow for a larger channel area and can result in higher current carrying capacity. Moreover, the geometry of the electrodes can influence the transistor's on and off ratio and switching behavior. Next, we want to talk about the post-deposition treatment, which including annealing and doping. Post-deposition treatment, also known as the post-deposition processing, refers to a set of thermal, chemical, or physical treatments that are applied to a thin film or coating material after it has been deposited onto a substrate. These treatments are used to modify the properties of the deposited film or layer to achieve better performance. Annealing at controlled temperatures can enhance the crystallinity and order of organic semiconductor films. This process can reduce trap states and increase charge carrier mobility. Vacuum annealing can eliminate unintentional doping. Also, before annealing, we may want to do surface treatment like the ultrasonic. And also, we want to annealing at a pure environment like the nitrogen atmosphere. Doping can shift the hormone towards the Fermi level for P doping and away from the Fermi level for N doping. Introducing dopants can modify the charge carrier concentration and improve device performance. However, doping must be carefully controlled to prevent excessive trap states or charge imbalance. Doping can modify the effective band gap of the semiconductor material. This can influence the energy levels of charge carriers and their mobility. Also, doping can induce the formation of more free charge carriers or the preservation of traps in the organic semiconductor and hence increase the conductivity. Doping may also introduce unfavorable effects to charge transport in organic semiconductors like the trapping, scattering, and instability. However, an increase in background carrier density may make the reduction of on and off ratio after chemical doping. This make less attractive for OFETs. Finally, I wanted to talk about the interface modification. The contact electrode and organic layer interface has a key influence on the contact resistance, while the dielectric organic layer interface has a key influence on carrier junction. So the interface modification is a very important process for OFET fabrication. Generally, there are three methods for interface modification. First is the surface treatment, then interfacial layer deposition, and the last is the annealing, just as mentioned above. First, I wanted to introduce the interfacial layer deposition. This means Additional thin layers of material may be deposited at the interfaces between different device layers. These layers can passivate defects, act as barrier layers, or facilitate charge transport. For example, a self-assembled monolayer may be deposited to modify the dielectric organic semiconductor interface. SAM can alter the surface chemistry and reduce trap states. We can see the image that VOPC is the interfacial layer deposition. Surface treatment with some chemical material for control the adhesion of the compressed powder to the substrate. Also, some physical method like cold isostatic pressing, hot isostatic pressing, used for compress the material into a certain form. There are 4 indicators that are very important to measure the performance of the OFET, which is the charge carrier mobility, threshold voltage, on and off current ratio, and the operating voltage. To sum up, fabrication methods, including the material selection, deposition, post-depositions, will directly influence the film morphology, which include the interface interaction, film roughness, molecular arrangement. The film morphology will influence the microscopic indicators like the trap density, disorder, band energy, carrier injection barriers. And these microscopic indicators will influence the device performance, including the operating voltage, threshold voltage, on and off ratios, etc. Thank you. That's all.